So we are now live. Fantastic. This is my first work with YouTube Live. I just got a message that says I can stream for up to 8 hours. So what time would that put us at? Like what I gotta make sure my time limit is okay. 12:22 a.m. All right, that sounds good. I'll try to keep it brief and cut off by 12:22 if I have to. I was really hoping to go until like 1:30, but I guess I can manage that. Um, so Test one review. I already talked to you about this in class a little bit, but the details are as follows. Oh, and by the way, I'm going to be putting this document, this PowerPoint that I've just slapped together on Canvas. It'll be under test review materials. Um, so that way, don't feel like you have to rush to jot down 90 minutes, parentheses, lab block, parentheses, 15 multiple choice, 2 points each, because then it's going to take me forever and a half to get through this here slideshow, and I've only got an 8 hour time limit. So, um, so this document will be on there. Feel free if you want to jot down some additional info or some examples. If you want me to walk through one of those, then I'm happy to do that as well by the end. But it is 90 minutes. It'll be 15 multiple choice questions, each worth 2 points. One lab-based question worth 10 points. 5 free response, 10 points each. And remember, like I said last time, I give a crap ton of partial credit. Crap ton being a scientific unit of measurement. Um, Partial credit. So, what that basically just means is you must show all your work. Once again, if you put the correct answer and the correct units, and that is all that you've put, you get 2 out of 10 points for that question. If you put the incorrect answer and the proper units, then you get 1 out of 10 points for that question. And if you somehow say the velocity was 10 meters when it was in fact 75 meters per second, then I'm afraid you get nothing. So, um, make sure that you show as much work as possible. Basically, it's this: the more you show me, the more points I can find for you. Basically, so if it feels like you're writing too much, you're probably doing it right. Um, if you decide to just kind of skip steps, then I'm not really going to be sure where you went wrong, and I'll have to take off more points. Yes, sir. You don't have to write every single little step down. Like basically, if you have 5x plus 3 equals 0, and then you end up with x equals negative 3 over 5, that's fine. You don't have to like show the subtract over step and all that. But you do need to at least set up the problem, show me what equation you're trying to use with it, um, and make it clear what variables are going where, I guess. And then just a brief overview of mathematical steps. If you skipped something like this to this, that's great. But if you just say you're asking for velocity, v equals v naught plus at, a equals 20 meters per second squared, then I'm going to be like, what? How? So make sure that you, I mean, be reasonable about it, I guess. You should be able to communicate that you know what you're doing. Right. Make sure you bring a calculator that is not your phone. Because believe it or not, you're not allowed to sit out there with your phone in front of you on this test, because I'm just a mean fart. Uh, and let me know ahead of time if you need to borrow one, because I only have like 10. So if everyone in the second block shows up and needs a calculator, there's not going to be enough to go around. But if you just shoot me a quick email, ask me to reserve one for you, you will be certain to have one here for the test. Some resources that are available to you as well, and these were recently uploaded to Canvas. You still have the videos that I've sent out to you. All of those are still available. You can go on and watch them as many times as you want. I've also taken the PowerPoints that I used while making the videos and just slapped those on Canvas as well. So you can download those and go through them at your leisure. There's also last year's Test 1 solutions are available. And old quiz solutions. Oh yeah, last year's test solutions. So when you log in and open that up, it'll just be a PDF. You'll see all the questions up top first, and then beneath the questions, if you scroll down, you'll see just my handwriting in red ink. with all the solutions. So that'll give you a snapshot of what will the test actually look like on my paper, what kind of questions are going to be asked, and the general level of difficulty. Since I'm releasing last year's test to you, I'm not going to have any of the same questions on this year's test, but it should give you at least some insight into the difficulty level that we're looking at, the problem types that we're looking at, and stuff like that. So if you can work through that and bring in questions in the next couple of days, that's great. Quizzes that I've given on Canvas, whether your class period took quiz 3 or not, you can log on to quiz 3 and look at the solutions there. Cool. And of course, old WebAssign problems. If you go onto WebAssign, you can always click past assignments and you can look at those old problems, see if you can rework some of them. I will say this, I typically have, WebAssigns are usually higher difficulty than tests for me, just because, woo! Because I figure with WebAssigns, you've got like 5 days and 10 tries. On a test, you've got 90 minutes and 1 try. So, right, yeah, for some of you, you've got 20 minutes and 10 tries, depending on when you open the WebAssign. But onward. So, let's get into the nitty-gritty of what you need to know. Metric prefixes. At the very least, you need to be able to convert these units right here. Not just what the metric prefixes are, but be able to convert between any of them. So you can write this metric staircase on your cheat sheet if you want to. Basically, where you are to where you need to go is the number of times you move the decimal point in that direction. That's not too bad. This whole mega equals 10 to the 6, kilo equals 10 to the 3rd, you can physically actually, if I see 7.2 kilometers, I can literally replace the kilo of the kilometers to 7.2 times 10 to the 3rd meters. And the k gets knocked out, gets replaced by times 10 to the 3rd, and that's that. So that's another way you can go about it as well. But all of these prefixes are fair game. Mega, we've not really run into much yet. That'll definitely be coming up later in the year. We've done some kilo with kilometers, centis, centimeters, millimeters, and we've not quite hit much micro and nano, but you need to know what those are for when we do come across those, like when we do light waves and sound waves and stuff like that. Cool. Speaking of unit conversions, you're going to want to basically look at where you are and look at where you need to go. So let's say you really liked that video I showed in class today of that car traveling at 100 kilometers per hour. And you liked it so much, you want to take some time to figure out, well, what is that speed in meters per second? Because those are base metric units, and man, I'm into base metric units. So you want to convert it. Basically, look at the units that you have, what's already in the numerator, and what's already in the denominator. Look at the units where you want to go. I would rather have meters in the numerator than kilometers. I'd rather have seconds in the denominator than hours. From there, you're just going to multiply it by several conversion factors. The conversion, oh man, I need to cough, but I don't want to do it into this microphone. Hold on.
That's so much better.
And we're back. So I want to get rid of my kilometers. Currently, they're in the numerator, so I'm going to have to put kilometers in the denominator. And take the time to go ahead and do this. Most people who called me over who had unit conversion questions hadn't actually written out the units themselves. They were just like, so I multiply by 60 and by 60 again. No, you divide by 60 and by 60. And it'll never be a question if you actually write this out. So if kilometers are in the numerator, I'll put them in the denominator to cancel it. So replace it with what I want in the numerator. There are 1,000 meters in every 1 kilometer. Okay. From here, I'm going to do the same thing with my time values, but since the unit I don't want is in the denominator right now, I have to put it in the numerator to cancel it and replace it with what I want in the denominator. There are 3,600 seconds in 1 hour. If you didn't know how many seconds there were in 1 hour, you can take a step to 60 minutes in 1 hour and then 60 seconds in 1 minute, and that'll work beautifully just as well. So by the time you punch this whole thing out, I don't know what that's going to come to. I didn't actually do this beforehand. Why would I think of things beforehand? So times 1,000 divided by 3,600, and boom, 27.8 meters per second or so. Cool. And I still, when I'm doing it, physically go through and mark out my units as I go to make sure that the 2 units that are not marked out are the ones that I actually want. Meters and seconds, and in this case it is. So be sure that you can do that. If I just give you some sort of conversion problem, you can run through it for me. Ooh, speaking of units, here are just some helpful hints that you can always use. This is a little bit of that dimensional analysis that I talked about earlier. Only units with only items with identical units can be added or subtracted. So I cannot add a meter and a kilometer, even though they're both units of distance. And the unit remains unchanged. So this can be helpful if you're going through, let's say, the position equation. Whoops. And dy equals d naught y plus v naught yt plus 1/2 ay. And you forget that the final t is squared, and you just write it like this. I can go through and double check myself. Let's say I forgot to write it on my cheat sheet, so I'm just pulling this out of memory. And I'm like, I think this is it, but I'm not really sure. I can go through and say, well, at the very end, each and every term needs to be in units of meters. Okay? Well, d naught y is already in meters, so I'm good. A velocity, that's in meters per second. A time is in seconds. Meters per second times second. Oh, cool. These seconds actually cancel out. So I'm just left with meters. All right, I'm in good shape. And then finally, 1/2 doesn't have units. Acceleration's in meters per second squared. And time is just in seconds. And this would simplify down to meters per second. Crap, I can't add meters to meters per second. So I know something's wrong with my equation. I need to multiply by time again, which means this t really needs to be squared for it to work. At that point, I'll end up in terms of meters. So if you're ever unsure about any equation that you're using, or did I actually plug the right variable into the right thing, check your units. That can always be a good hint for you as well. Which, by the way, any units can be multiplied or divided together. So kind of like I just showed up there, multiplying meters per second squared by seconds squared will get you meters. Cool. Then we talked about significant figures. Yeah. Significant figures are going to come up a lot more in lab settings rather than theory. But still, it's important to know, even if you're just going through theoretically. Basically, it's how confident are you in your solution? If you report a measured acceleration to me back to like 7 decimal places, I can promise you we did not measure it that precisely. It's telling the world how confident you are in this thing. So, as a reminder, any non-zero digit is significant. Those are just the digits 1 through 9. Those are really easy. Go ahead and check them off right away. If you're on the left of a decimal point, which means, I've got some values here and a decimal point, and then maybe other values. So 102.1.9. It's going to be significant if it is between any other significant figures. Nice. So this one is. It gets a little bit funky if you're, like, say, the number 1000. That could be one significant figure, that could be two, that could be three, that could be zero. No, that's not right. It could be four. It couldn't be zero because one's always significant. Yeah, so that's ambiguous. Either add a decimal point, in which case this zero would be significant and all the other zeros therefore are, or honestly, just use scientific notation. If you've got a number that's ending in a zero and we're asking for the number of sig figs of it, just put it in scientific notation, because all of a sudden the decimal point is after the first actual sig fig that's not a zero. So I could write this as 1.00 times 10 to the third, in which case that's obviously just 3 sig figs, and then it's not ambiguous anymore. I'm never going to ask you a question where I give you like 1020 and ask you to tell me the number of sig figs. Yeah. To the right of a decimal point, basically it's this. As soon as you get a non-zero digit and any other zero is to the right of the decimal point, those zeros are going to be significant automatically. But you have to wait until you get to your non-zero value. Until you get to your first non-zero value. So if the number begins with 0, 0.000, all those leading zeros, while they matter for the raw value of the number, I don't want, when I say insignificant, I don't want you to think they don't matter, so I don't have to include them. No, they matter. It's just, in scientific terms, it's not a significant figure. So these opening zeros, no, 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 no. Until you get to the 2, yes. Then any zeros to the right of the decimal point beyond that 2 are going to be considered significant. These two are because they're between the 2 and the 3. So since they are nested between 2 sig figs, they're significant themselves. This last one is because it's a final 0 to the right of the decimal point. And the only reason I would want to include that is to show you that I know this value is 0. Otherwise, I would just lop it off and not even write it. So that is significant there. And if I wanted to write this in scientific notation, 2.0030, that would be times 10 to the negative 1, 2, 3, 4, times 10 to the negative 4. Then I'd still have the same number of significant figures. The 2 is, the final 0 is, the 3 is, and everything in between. So at any point, feel free to just change any number to scientific notation, even if it's the stupidest thing. If it's like 10 and it's 1 times 10 to the 1th power, you could do that and either include just the 1 or the 1.0, and that way I'll know if that 0 is significant or not. Cool. So when you're adding and subtracting significant figures, well, when you're adding and subtracting any two numbers, you actually don't care about significant figures. All you care about are decimal points, and that's it. So look at the number with the least amount of decimal points. If I've got, let's say, 2.1 plus 3.02 plus 3.02, I'm going to round it so that my final answer just has one decimal point. Because of my two numbers coming in, 2.1 has the least number of decimal points, being 1. And so that's what I'll round my answer to. I don't even count sig figs. I don't care about zeros. I don't care about anything else. Just the number of decimal points that are reported in the incoming number when you're adding and subtracting. When you're multiplying and dividing, then you look at sig figs, not decimal points. So if I multiplied 10.0 times 3.1 both of them end at the first decimal point, but I don't care about decimal points. The final answer is going to be just 31 exactly, because this number had 2 sig figs, this one had 3, so I'm going to round it to 2, because that was the least number of sig figs I had coming in. All right. So this is all still just background mathematics-y stuff. Any questions about what we've done so far? Unit conversion, sig figs. Coolio. Then let's keep going. Vectors. Vectors were what we did next. Basically, they're anything that has a magnitude and a direction. And it's usually represented by a ray. And I swear I moved this picture down. This should say usually angle above the horizontal. Is typically how we measure it, or counterclockwise from the x-axis. Not always. They can give you some direction, like I could have a pendulum hanging from the ceiling, and I could give you this angle here, and there's a vector for you. But typically, it'll be something like this. Right. And a negative in front of a vector, that's just going to change its direction by 180 degrees. So kind of like when we get to two-dimensional projectile motion, something moving up has a positive velocity, because I like to say up is positive. Its acceleration would be negative 9.81 meters per second squared. That means my vector for acceleration is flipped 180 degrees, and therefore it's pointing downward. Since acceleration is down, that's how I like it. So that's all that a negative does for vectors. In reality, the best way of saying this would not be negative 9.81, it would just be 9.81 meters per second squared down. Then you've got a magnitude and a direction. So again, a magnitude is just its absolute value. There's not really such a thing as a negative vector. It's just a vector pointing in the opposite direction that makes you think negative. Cool. I always say cool when I get to the end of these slides, don't I? I'm going to stop that. I need a different catchphrase. What should I say at the end of the next slide that's not cool? Never mind. Meanwhile, scalars. Scalars are anything that are not vectors. They just have a magnitude. We've not really dealt with a whole lot of... you could kind of count time sort of as a scalar, unless you start wanting to get really like general relativityness with it, where we treat time as a different dimension almost, and you can go forward or backward in time and stuff like that. Let's not do that in the first month of physics, though. Instead, you can kind of treat it as a scalar. Mass is totally a scalar. 75 kilograms to the right and up doesn't make any sense. Just 75 kilograms, that's a mass. Done. Or most counts that you have. There are 8 computers at these lab stations. Okay. Cool. No, I did it! No. Oh, I'm going to be so self-conscious about that for the rest of this time. One of the most helpful things that you're going to want in order to deal with vectors is right triangle trig. Anytime you've got a vector and some sort of an angle, you can create a right triangle out of it. One side will be adjacent to your angle, one side will be opposite, and one side will be the hypotenuse. Typically, the vector itself will be the hypotenuse. A few exceptions. I'll say full vector here. A few exceptions. If I have a vector that's pointing just to the right, and I'll say vector A equals 10 million miles to the right. Okay. My x component is just going to be 10 million miles. My y component is going to be 0. Because it's not going up at all, it's not going down at all. So in that case, there's literally no need to write out a triangle. I can break it down in x and y components without doing any sort of trigonometry. Same deal if I've got something just up and just down. Let me just do this. If it's just up and it's, let's say, 0.003 meters per second is my velocity. That means my y velocity is 0.003 meters per second. My x velocity is 0 because it's not moving to the left or right at all. But it's for those little more complicated vectors that are not necessarily pointing up or down. That's where the vector itself will be the hypotenuse. And you got to make a right triangle out of it, find the x component, find the y component. Yeah. So make sure you know SOHCAHTOA in order to do this. Lots of different ways you can do it. Some old horse caught another horse, taking oats away, and there are many more that I will just let you come up with on your own. Awesome. I didn't say cool. So once again, vectors can be broken into x and y components. Once you have your first vector, just draw a little line that goes from the start of the vector to just under where it ends. Make sure that line doesn't go up or down at all. That's the base of your triangle. That is your x component. Draw a little line from the end of your x component all the way up to the end of the vector. This is a vector that goes up the same distance that vector A does, but it doesn't have any of the left or right parts to it. That'll be your y component. Once you've set up your triangle, take note of where your right triangle is. Make note of where any given angle to you is. A lot of times the angle that's given is just this one right here, but not always. At this point, you're probably used to x getting the cosine because that's the angle given to you, and y getting the sine. Again, that's not always going to be the case. If I gave you that upper angle instead, y would get cosine, x would get sine. So just be aware and actually draw the pictures. When I was a student here in physics, I remember my teacher yelling to draw pictures all the time. I generally ignored him. I generally got problems wrong. I would draw a picture and then it would work out better for me. And now, that was over 10 years ago at this point. Now that I've gone through and gotten a bachelor's in physics and continued to do this for all these years, I still have to draw a picture for myself at the start of any given problem, always. So, swagalicious. That's for that slide. Now, if you, that one's a keeper? Okay, cool. Vector addition. After we talked about just taking vectors and breaking them into x and y components, we talked about how to add two different vectors together. This is where we went back to first grade. I gave you some scissors and pieces of paper, and you cut things out and you taped them together, and it looked really pretty, and you drew on it, and that was great. The way to handle vector addition is, once again, the end of vector A is the beginning of vector B. And remember, the arrowhead just goes on the end there. So there's my vector A from the last slide, and I'm going to slap vector B so it picks up where vector A left off. As the ancient saying goes, where one vector ends, so another must always begin. And then finally, your resultant vector will connect from the very, very beginning to the very, very end of these two vectors put together. And if you notice, vector A, I'm going to do this in blue, has its own x component. That'll be ax. It has its own y component, ay. Vector B has its own x component. Call that bx. It has its own y component. I'll call that by. When you bring around, oh man, it's going to get deleted when I go to the next, hold on. Copy. Okay. when you bring your resultant vector into it, and you actually, oh, no, edit mode. What have I done? Okay. When you bring your old x and y components back into the fray, there, you can also form, and I'll do this in orange since that's the color of my resultant vector. I can form my resultant x here. I'll call that Rx. And check it out. It's just the length of A plus the length of B all together. So Rx equals AX plus BX. Nice. And it'll be the same thing in the y direction. Let me take out these little lines I drew. Okay. Look at AY. It went up. Oh, I was just deleted that whole thing. AY went up this whole way. BY went up this little way. Combine them together. I've got my RY. AX plus BX. AY plus BY. And that's a lot to keep track of, all on one. That's just the jumbled mess of a drawing right now. So let me clean it up a bit. Your final resultant vector will have its own x and y components that look like this. And all those x and y components actually are, it's just the sum of the x components of the original vector, sum of the y components of the original vector. Nice. So yeah, another way of thinking about it is this. Only identical units can be added. Additionally, only identical components can be added. So I cannot add a vector, well, just add it in terms of addition as you know it. 2 plus 3 is 5. I almost messed that up. 2 plus, yeah, man, I've got a degree in physics, but 2 plus 3, whew, that's a tough one. So only identical components can be added. So basically, here's what I recommend you do. You don't have to always draw out your two vectors, draw them tip to tail, if you don't want to, because that is pretty tedious and it gets pretty messy. Instead, I would look at each vector by itself, grab vector A and forget vector B even exists, find AX and AY. Then do the same thing with B. Grab vector B, forget that A even exists, that was so a few minutes ago, find BX and BY. After that, then take a step back and look at everything you got. Grab your x components of both vectors and smash them together, find the sum. Grab the y components of both vectors, smash them together, and find the sum. Now you've got the resultant x and y, Pythagorean theorem it, and you are done. And then you'll use trigonometry to find any necessary angle that's there. So, take your original vector, break it down. Take another vector, break it down. Take as many vectors as you're adding together, break them all down. And then gather up all your x's in one bucket, set that aside. Gather up all your y's in one bucket, set that aside, find the sum. And then Pythagorean theorem from there. Since it's my first YouTube thing, I'm just going to pop back over, look at the other screen, make sure it's still broadcasting. Hey, it is. I am screenshotting. Great. All right, then I'm going to head back to this and keep on going. Then finally, Mr. Martin's faux mathematics class ended, and we actually started talking about physics when we started moving. So a few vectors that are going to be really useful to use. One is displacement. That's basically how far are you from where you started. It's different than total distance traveled. Total distance traveled is just, you're just going to straight up add. So if I went like 3 meters this way, and then I cut up and I went 5 meters this way, I can guarantee you that I'm not 8 meters from my starting point, even though my feet traveled 8 meters. So displacement is how far from the beginning are you to the end. And we use that a lot in the distance equation, even though you haven't noticed it. Today in class, we talked, or Friday, for some blocks. We talked about when you launched a projectile from a muzzle that was at the equal height to the table. And we found the difference between dy and d naught y. That was quite literally, it ended up being 0, and it was just the displacement from my original y height. So in terms of the y-axis, my total displacement was 0, even though it traveled up and back down. The total displacement, when all was said and done, came to 0. For elevation, that is. For the x direction, there was some displacement, and that was not 0. And that's what you were calculating. Velocity, meanwhile, is the rate of change of distance. So if I'm walking on that path, how quickly I do it is my velocity, and in what direction. If my velocity is 0, my position does not change. And then finally, there's acceleration. This is going to be the rate of change of your velocity. So if I'm walking at a constant speed, yes, I'm moving. Maybe I'm moving in the positive direction. Maybe I'm moving in the negative direction. I don't know. But if it doesn't change, my acceleration is 0. If it does change, if I'm running in the x direction and I go from 2 meters per second to 4 meters per second, then I've accelerated in the x direction. All right. Then we started talking equations. Here's your position equation. D equals d naught plus v naught t plus 1/2 at squared. Here's where d is your position at any given moment in time. So position at time t. That'll be measured in meters here. D naught is going to be my starting position. And that's going to be, just where did I begin? In meters. A lot of times that can be 0, because when you solve physics problems, you get to set what the 0 position is. You get to set up your own little XY coordinate frame, and everything else that happens becomes little points in your XY scale. So a lot of times it's useful to set the starting or ending position at 0. That way you don't have to worry about it. And the more things that are 0, the more I like these problems. V naught is going to be your starting velocity. Notice how in the position equation, it doesn't matter how fast you end up going. All that matters is your starting velocity in meters per second. That's because any change that happens gets picked up by this little doohickey, the acceleration in meters per second squared. One half is 1/2, and time are your two little t variables that are showing up here. So from the moment the action happened, the timer starts at 0 and it counts up. How far did I travel in 1.7 seconds? How far did I travel in a million years if I keep going in this direction? You can just plug these values in here. Make sure as you do it that you're paying attention to your units. If I've got velocity in kilometers per hour, my position in meters, my acceleration in meters per second squared, that's not going to fly. And some people ran into some issues with that on the lab because they kept their final position in centimeters, but they still used 9.81, which is meters per second squared. The units weren't lining up. Usually it's best to just go back to your base units at all times. All right. Ooh. Here's your velocity equation. Once again, v, that's just your final velocity or velocity at times t in meters per second. How fast am I going at this moment? V naught, once again, will just be your starting velocity. How fast was I going when this whole thing started, when t was 0? A is just your acceleration That'll be in meters per second squared. And t, that'll be time in seconds. Okay. So you'll probably want to jot down the velocity equation and position equation. And finally, there's the combo equation. This is your final velocity, or velocity at time t, in meters per second. Your initial velocity, also in meters per second. And you're finding the difference of the squared of the two of them. That'll equal 2 times my acceleration in meters per second squared times the change in distance, or change in position, your overall displacement. What is your final position minus your initial position? Excellent. This is kind of useful if you're asked to find, like, let's say you're given a starting and ending velocity and the total distance traveled. They want to know the acceleration. This is just a useful equation to jump to if you don't want to bother calculating time first. A lot of times the combo equation you can avoid if you want to by going to the velocity equation first, solving for time, hopping over to the distance equation, plugging your time value in there, and that's fine. Whatever it is that you, whatever floats your boat, whatever cooks your cookie, I guess. Then we talked free fall, and we've been doing almost exclusively free fall problems since, with a few exceptions. So, as a reminder, the moment that object loses contact with all other objects and it's just up in the air, it is in free fall. If it is on Earth, which most of the objects that you're going to be tossing around in my class will be on Earth, except for a very special field trip that I'm going to arrange to space. It'll have a magnitude acceleration 9.81 meters per second squared in the downward y direction. And again, the moment it loses contact with anything else, I don't care if it's moving up, I don't care if it's moving down, I don't care if it's at the top and not moving, I don't care if it's moving to the right and up. The moment it loses contact with anything else, it is in free fall. Oh, a couple of reminders, and apparently, once again, sometime between a few minutes ago when I edited this and when I'm now doing the slideshow, the words got stuck behind the picture. So, assuming no air resistance, which is basically the case, the initial x velocity, here's what, I'm going to go ahead and fix this slide, because I'm not going to try to guess. Hold on a moment. So, any object in free fall has an x component of velocity equal to the initial x component, because the acceleration in the x direction is always 0. In free fall only. If I'm sprinting in a race and I take off from the starting point and I run horizontally and I speed up, yeah, I've got an x acceleration. But if I'm loading myself into a cannon and I fire and then I go flying up into the air, from that point on, my x acceleration is 0 meters per second squared. And at the top of its free-falling trajectory, it has a vertical component, Vy, equal to 0 meters per second. At the same time, Vx is whatever the x velocity started as. So if I ever asked you, hey, how fast was this thing moving? How fast was it moving up at the top of its trajectory? Find the initial x velocity. What is wrong with me? Find the initial x velocity from when it launched. There's your answer, because the y drops to 0. Okay. So look at the start of the launch, break into x and y components, grab the x component. That's how fast it's moving at the very top of its trajectory. And then it picks up y speed as it falls downward after that. All right. Since we're doing motion in 2 dimensions, projectile motion, all that kind of good stuff, any velocity vector that I have can at any point be broken into x and y components. And once you do break it into x and y components, you'll use these same equations of motion, the exact same ones, but you'll put little subscript x's and little subscript y's throughout. Just to remind yourself that I'm only dealing vertically right now, or I'm only dealing horizontally right now. It's kind of like what I talked about earlier today when I was running and threw the ball straight up in the air. You saw x and y components of that ball's motion. I just saw y components of that ball's motion. But if we broke it down, any mathematics you do with the y component would turn out identical with mathematics I did with the y component. What would just be different would be x's. Usually, for projectile freefall problems, these x equations simplify down simply because the acceleration is 0. So it makes it a lot easier. Right? So this is just sort of a little summary page of freefall in 2 dimensions, put a little bit more briefly. Things you can always grab, and it's not going to necessarily be given in the problem. I won't necessarily say it has a downward acceleration of 9.81 meters per second squared. It'll just be assumed that you know that if it's up in the air. So you can always treat that as a y. I won't, and it'll be downward, so maybe you're going to want to throw a little negative in front of that if you're used to up being positive. The y velocity at the highest point, all one word, is 0. The x component of velocity at the highest point is whatever it started out as. No horizontal x acceleration, ax equals 0 meters per second squared, and nice. So those are kind of the main takeaways for free fall and stuff you can always grab in order to do these problems. I'm going to stop again for a second. Any other questions about these motion equations or free fall or anything? Okay. Make sure you're somewhat comfortable with motion graphs. If I show you a graph and ask you what's happening at this point in time, make sure you can tell me. So a position versus time, the slope is going to be the velocity because it's rise over run. Odds are I'll have position on my y-axis, time on my x-axis, and rise over run would give me meters over seconds. That's my velocity. So if I gave you, let's say, a position versus time graph and said at what point was it not moving, look for the slope to be 0. Okay. If I gave you a velocity versus time graph and I said at what point is it not moving, look for the y value to be 0, not the slope. Because now the y-axis has my velocity charted on it. The slope of a velocity versus time graph is an acceleration. So if you see a totally flat velocity versus time graph on any value other than 0, you're still moving. You're just moving at a constant speed. If you see any flat value on a position versus time graph, no matter what it is, you're not moving because the velocity is 0. And then pay attention to signs. If I've got acceleration and velocity that have the same sign, that means my y value is positive and my slope is positive. I am speeding up. Or my y value is negative and my slope is negative. I'm speeding up, but in the negative direction. But if the signs are opposite, like let's say I've got a positive slope but it's down below where the y values are negative, then I'm slowing down. I'm moving still in the negative direction, but I'm slowing down, getting closer and closer to 0. Versus if I've got a positive y value but a downward slope, then I'm slowing down. I'm still moving in the positive direction, but I'm slowing down, getting closer and closer to 0. It was lab 2 that you did that you walked these graphs back and forth. So you can always glance at that as well. I think those are the main takeaways. Let me just make sure. Oh, then I have general problem solving. I'll talk about that in just a second. Any graph questions or anything like that? When these graphs are thrown at you, generally the velocity graphs give people more trouble than the position ones. So let me know if you look back at graphs and yeah. Sure. You are. Sorry, for those of you who were listening at home, you probably didn't hear that just now, I realize. The question was, if your velocity versus time graph is negative and a negative slope, so something like here, this region right here, that means I've got a negative y value and a negative slope. And if you think about it, I'm getting farther and farther away from my 0 line. So it means I'm speeding up. Up here, I've got a negative, I've got a positive y-axis, a y value, and a negative slope, so I'm slowing down, getting closer and closer to 0, which is where I stop. Again, on a velocity versus time graph. I don't necessarily stop at 0 on a position versus time graph. So this would actually be a velocity graph of if I threw a ball straight up in the air, at first it would have some positive upward motion. It would slow down. It would stop. Then it would begin to fall downward like this, all with a constant acceleration of 9.81 meters per second squared, hence the constant slope. Okay. And finally, my last little slide of this thing. For problem solving techniques, draw a picture. Like I said, I used to hate doing it. Now I cannot start working problems without it. Doesn't have to be pretty. Label your coordinate frame. Where is 0 on your x and y axis? Once you've done that, identify a known variable, list what you need. So your knowns versus your needs. Make sure you convert all your values to base units. And from there, grab an equation and solve for whatever your unknown variable is. Sometimes it'll take 2 equations. I need to figure out the amount of time it takes first, then I can grab that time value and fling it into another equation to solve for distance or something like that. So grab as many equations as you think may be helpful and then try to parse it out. Basically, even if you solve for what the problem doesn't ask for, that's at least more information that you now know that you can use to solve for what you need. So don't be afraid to solve for useless things as you go. Okay. I think you all do just fine. Again, probably the most useful thing to look at is going to be last year's test, and that is presently up on Canvas. Once again, I'm going to add this PowerPoint as well. I'll try to fix up those slides that had issues and then add it, and then just flag me down if you have any questions. Excellent. Let me exit out of this. Stop broadcast. Did that work?